So if you don't want to be on the YouTube, then you switch off your video, feel free. But if you don't mind, then...
Okay, here we are.
Okay, great. And I'm just a quick check to see if I have... Okay, so Giovanni, I don't have permission to switch off the YouTube. So if you leave and you want me to switch anything off, otherwise I just exit at some point. And then...
Yeah, there's a stop live stream button.
Yeah, I don't have that. I think only the host has that.
Okay, you will be host at some point, and then if you end the meeting, it will be stopped.
Okay. Yeah. Now, I think I don't need 2 hours actually. I think hopefully 1 hour or so. But then again, I also said that last week, and then I talked for 1.5 hours. So you know. But anyways, welcome everyone. I'm very happy to see you again. For the second part of the PLUMED Masterclass 22.9 on using path collector variables to sample free energy landscapes and find reaction mechanisms. Happy to hear that you managed to try and do a couple of these exercises. And so the plan for today is just to go through. I'm a little bit less organized as last week, as in the sense that I didn't prepare any slides or anything. I just have some results that I would like to discuss. And yeah, I like it if we're interactive. So feel free to ask questions anytime, because I'm also more than happy to just try out a few things. If you say, oh, I didn't get it to work with these parameters, then yeah, just tell me, and we'll see if we can work it out together. I think that's most useful for everyone, because me just showing what you should have gotten, yeah, I don't know how helpful that is. Okay, so here we go. Well, let's start really from the very beginning. And I start, of course, by sharing my screen. Here we go, share screen. Now, so we're here in plumed.org with here the PLUMED Masterclass, and yeah, using path collector variables to find the reaction mechanisms in complex free energy landscapes. Now, the way to find the exercises was to click on doc here and then go to the development version. And then on the left, you see tutorials, and starts with a series on of this year, 22, 1, 2, 3, 4, 5, 6, 7, 9. We're here. So, okay. So this you should have all gotten, and you should have been able to clone the exercises, and then yeah, it unpacks in a directory PLUMED, and it has a version of PLUMED, not the latest version 2.3.0, because there's our in-house developed version of the path CV CPP file, and also the PLUMED MD, which we're using for this exercise. But as I said last week, if you have a more recent version of PLUMED, PLUMED 22.8, sorry, not 22, PLUMED 2.8, for example, then of course it also has a path CV implementation. It's just that the input file is slightly different, and if you try that one instead, then I'm also more than happy to discuss that if you have questions about that. But yeah, to keep things easy, I thought we all use the same version, and yeah, we'll just look at how you can use it, and yeah, we discuss the results. So I hope you all managed to compile a version of PLUMED and get it to work. And then there were 5 exercises, aiming to find the reaction path and a free energy profile on this analytic potential, the famous Muller-Brown potential, which is very old, and is actually supposed to represent a chemical reaction. I forgot which one. It's based on a paper that you can look up, reference 8 here. And And the reason why we do that is of course that it's very quick. So it's great for testing. So we can quickly try all sorts of parameterizations and see where it goes wrong and see where it goes well. And you can run it on a reasonably fast laptop, and you'll have a result in 30 seconds, which is perfect. But as I said last time, I'm also more than happy to discuss real applications of molecular systems. So if you spend this week fighting with your own application, your own molecular transition and MD engine, then we can also discuss that. Okay, but let's start first with this Muller-Brown potential. So it's a two-dimensional potential that has an x and y coordinate here, which are then the CVs, the collective variables. So we have two collective variables. One runs from, in this space, -5.1.5 in some arbitrary units, and the other one from -0.5 to 2.5. And there's three minima. There's this reactant minimum here at 0.50. Then there's the product state at, let's say, -0.5, 1.5, right? And that's connected to this bottleneck here. And there's actually a very small minimum here as well, right? So there's like an intermediate state. So you go from here to here and then through this bottleneck, and then you arrive in the product state. That's the idea. Okay. Now, so normally you would patch PLUMED to an MD engine like GROMACS or OpenMM or CP2K or LAMPS, for example. There's a whole list. But we actually use PLUMED standalone in this exercise using one of the built-in features, which is called PES MD. And PES stands for potential energy surface, and in fact this is a potential energy surface, and MD stands for molecular dynamics, although there's no molecules involved in this exercise. No molecules were harmed in this masterclass, and we're just doing a dynamics, not really molecular dynamics, but we do a dynamics on this potential energy landscape, so hence PES MD. Right, now, so this, as I said, 5 exercises. In the first one we just do an unbiased molecular dynamics simulation. The second one, we will use two-dimensional metadynamics using the two collective variables. The third one, we will do a bias simulation along a fixed path that goes from the reactor state to the product state. And in the fourth exercise, we're going to optimize that path to find the minimum free energy path, say. And then there's an extra exercise, exercise number 5, where we will play a little bit with this multiple walker implementation. So see if we can get the parallel version to work. So that's the plan for today. And I'm going to start with exercise number 1. Now, maybe I briefly show you at least how it looks on my screen. So if you do a git clone, you will get this masterclass directory, right? Masterclass 2201. You go inside, and then there should be 2 directories. One is called PLUMED, and the other one is exercises. Now the PLUMED has an install script. If you run it, it will unpack this zipped tar file into the usual PLUMED source and documentation, everything. And then there's a few extra files: path CV, CPP, and PES CPP, which you can also find on my personal GitHub page. And so these have the latest versions of things that are developed in Amsterdam, actually. As I said, you can also use the one that is already inside PLUMED. I think it should have almost everything except maybe the multiple walker stuff. I'm not sure if that's already implemented in the official release of PLUMED. So that's why I like to use this one in this exercise. But, well, that's just a matter of taste. So, as I already said, you should have installed this. I hope you all managed to do that. I don't want to talk about installation. I want to talk about the exercises and how this path stuff works. So if you go in that direction, in directory in this folder, exercises, interesting. There's only 4 directories here. Am I doing something wrong? Okay, maybe I should do another git clone. Anyways, no problem. We'll get there in a minute. I have somewhere the 5th exercise as well, I think, for the Maple Walker stuff. But let's start with this. And here's this potential.dot file, which we need to. That's the potential energy landscape. You know, it's just a file with numbers. It's a 100 by 100 grid. If you open it, you can see that with an x and a y coordinate, and then this is an energy in some units, right? So it's just an yeah. After every update, so after every 100 lines, there's a white line, which is the way that the new plot likes to read contour plots, contour data. So that's why that is. Okay, so let's go in the first directory, number 0. And that's where we should do the MD exercise. Maybe I first quickly read the exercise. Okay, the first exercise is found in this folder 0 MD. And yeah, we just want to get acquainted with this PLUMED MD engine. Understand these input files and some plotting of output. I'll be using NuPlot actually, but I also have an implementation in Jupyter Notebook. So you know, if you want to discuss how it should look like in Jupyter or Python, say, using matplotlib, then we can also discuss that. Okay, so now there are some scripts inside. One of them is run.me. The scripts are not executable yet, so if you want to use the scripts, then you should give them executable permission, and then you can run it. So let's give that a try. Actually, there's a few more files. Maybe we should have a quick look at the files. Here's again this potential.dot that we're using to run the MD on. If we look in run.me, actually it just has one line, which is the command to execute the simulation using PLUMED, right? So it goes into the directory in which we installed PLUMED. So this is the PLUMED executable, and then PESMD is telling it that we're going to run the standalone MD engine on this potential energy landscape. There's an input file, and it should generate an output file. So the input file is here, right? So and then there's one more input file, plume.dot. So if you don't tell PLUMED what the input file name is, then this is the default name actually of the PLUMED directives. So input is just an input file for this PESMD feature, but everything else that has to do with PLUMED, so defining collective variables, defining a bias, defining all sorts of functions, giving output of collective variables and stuff like that. That's of course all in this plume.dot file, which you can give another name if you want, but the default name is plume.dot. And then there's one more file, plot_cvs. So all files that you'll see in my exercises that start with plot are scripts for running it with NuPlot. Now, as I said, if you run something else, then NuPlot for plotting, like XMGrace or Matplotlib, then you don't need those files. Okay, now first quickly have a look at the input file for the PESMD, which looks like this, right? And of course, you can find this also in the manual. So let's have a quick look at the manual. Now, the manual that you're seeing here is the one that comes with the installation. So if you download, if you did the git clone and you installed it and you did the make doc as well, then you should have the whole HTML documentation online. And in fact, if you look here in my browser, it says, file. So this is local, right? So you have that as well. So you can just go into Plumed 2.3.0. There's a directory user doc, which has all the HTML files. And if you open index.html, you'll see this page. So here's the, in collective variables, there's going to be functions, and there's path, the path CV that we'll be discussing today. And yeah, I see path CV. You could say, why is that not a collective variable? It's called path collective variable, right? So clearly it should be under collective variables. It should be under CV documentation. So why is it not here? Actually, if you look here, there is actually something about paths, I think, or not. No, not in this version. Well, if you look in the online version, then there is. So I could quickly go here. So this is now the online version of the latest version, and I go to collective variables and CVs, and yeah, for example, here's path, and here's path MSD, which is the same stuff. But the version that we're going to be using, which is my personal version, is in function. And why is that? It's just a matter of taste, but I really see this object, path CV, as a function of collective variables, and that's why I put it in function. And we treat it in the same way as the combine, for example, in which you combine functions in a linear combination, and path CV is doing the same thing. It combines collective variables in a nonlinear fashion, right? Or linear, but if we optimize the path, it's usually nonlinear. Okay, so that's about the path CV, but actually I want to first show you something else. In the command line tools here, there's all the standalone things built in Plumed that you can use. The driver is very nice. I'm not going to talk about that one. The manual as well. This is the one I want to talk about, PLUMED MD. So if I click on this one, it will tell you how to run it. So Plumed, PLUMED MD, and you give it an input file. And then it tells you what should be in this input file, right? So here's there's a little example, etc. Right? So that's what we're going to use. And okay, so back to my input file. This is the one that was in the exercise. And I think it's quite human readable, right? It's pretty clear what's happening here. N step is the number of MD steps that we're going to do, 500,000. There's a temperature in some weird units, right? So it's reduced units. So 0.5 is a good temperature. It's a low temperature, or it's clearly not kelvins, right? Since there's only one, particle, we can call it a particle. So a two-dimensional particle running on this PES that doesn't hit anything. It's going to be a very ballistic motion if we would just run it like that with the Newtonian dynamics. So instead, we're using a Langevin dynamics with a friction and random forces to mimic interaction with some environment, like a bath, right? And so here we can decide what sort of friction we're going to use. I don't want to discuss it too much, but it's basically like a thermostat. So how strong is it coupled to a thermostat, say? So it's a Langevin thermostat, and the friction is 0.1. I invite you very much to play with that if you haven't done it yet. So just see what happens if you make it 1 or 10 or 0, right? And you will see that the motion of the particle will change. If you increase this number, it will become more erratic. You get a more stochastic dynamics. This is the time step, T step, 0.001. It's a small time step. Also, play with these numbers, right? See what happens. Can you break the integrator if you make it, 100, say? The answer is yes, actually. So here it reads the potential.dat file, the PES that it's going to run on. We give it initial coordinates, so pos x in it 0.6 and y is 0.0. IDOM is just a random number seed, and this wrap atoms false is not a relevant thing, but you still have to set it. It just means that the thing cannot run off the PES, but it cannot run off the PES anyways because we were using walls actually in the PES. So we can run this. We would like some output as well, and this will already produce some output. But we would also like to print collective variables, and the collective variables in this case are just the x and y coordinates of this two-dimensional particle. And so we use this plumed.dat file to define some things that then later on we will be able to bias as well. And how is that done on a two-dimensional particle? So what are the collective variables, you may ask? And in this case, well, the particle position actually represents the collective variables, right? So how do we do that? Well, it's done in a funny way. If you look at this, you'll see we define an object called CV, collective variable, right? Which is actually a two-dimensional object because it's a distance splitting components, right? So maybe you already know this, but in Plumed you can define a distance between two atoms, say, but then you can also split it in the components, which is usually 3 components for a three-dimensional system. So you have an x, you have a distance projected in x, y, and z. Normally, here we have a two-dimensional particle, so we only have 2 components, x and y. And so what are these 2 atoms then? Well, the PES MD actually has 2 atoms, which is kind of funny. Of course, we will only see one of them going around, which is particle number 2. And then there's a first particle, which just sits still. It can't move. It sits at the origin. And then we can define a distance between the 2 particles. And then the distance, the components of this distance are just the positions of that particle, right? Because it's the distance with respect to the particle that sits at 0, 0. So that's just a technicality that from now on we can ignore. But that's how we, how we define some collective variables, even though there's only just one particle moving. The other 2 lines that after this you can also ignore, but they have to be there, are a lower and upper walls set at, well, the lower walls are working on collective variable, the x component and the y component, so our 2 collective variables at minus 0.5 and 0.5. And well, what is that then? That's so here's our PES, and the x-axis runs from minus 0.5 to 0.5, and the other one from y-axis from minus 0.5 to 2.5. And so we have this lower wall at minus 0.5, 0.5, which is this point here, right? So it cannot go off in that direction or down. And then we have an upper wall here that goes all the way to plus 0.5, which is here. And the other one goes all the way to 2.5 here, so it cannot go off the map, right? So that's what these walls do. Kappa is a force constant, so it really cannot go off the wall. I mean, so this is the same units as this temperature of 0.5, right? So it's all defined in, well, let's, I don't know, Kelvins or KBs or something. Yeah, and then we print them. So we print the value of the collective variables every 100 MD steps to a file called callvar.out. Now let's run it. I already made mine executable, right? So you see it's executable permission. If you haven't done that, then you can do that by just writing change mod plus x run me. And then you should be able to run it. And if you run it, interesting. Oh, I'm in the wrong directory. Yeah, this was my example, but I should be here actually. Sorry for that. Exercises, there is not a copy. Ah, and look, here's also my multiple walkers that I was worrying about. Okay, anyways, 0. Yeah. Okay, so I run this. Actually, I already run it. You see already some output files, but let's run it again just to show you how fast it goes. Done. So, and it created an output file and a colvar.out file. And since I already ran before, 2 times actually, it created some backup files, right? So this is another very nice thing of Plumed. It immediately recognizes that there were already some output files. It doesn't want to overwrite them, so it copies them into a backup file, which is very handy. Of course, you should clean up at some point, but at least you don't have to be afraid that you accidentally overwrite stuff. Now, let's first have a quick look at the output. It's not very exciting, but you should have seen it at least once in your life. It just first echoes the input file. So this is what we've been running. And then it starts to parse the input files, and it just tells you basically what they are. So first we define the units, we define this distance, we define lower walls, we define upper walls, right? Keep on going, keep on going. We define the print statement. It just echoes all the things that we are setting here. And here it's running. So it quickly ran. It tells us to cite some stuff. And here we were, this is just some technicalities. So this is not so exciting, but it's important for, especially development and but also seeing if it crashes, what happened. Did we do a typo in the input file or something like that? The more exciting output is actually in the colvar file, the colvar out file. Let's not do a count because it's big, more. And so this is what it prints, just 3 columns. There's always a nice header file telling you what are we looking at. The first column is the time, and the second and the third are these collective variables, or the x and y coordinates of our 2-dimensional particle. And let's plot them. So we did many steps. How many steps did we do? 500,000 steps we did, and so it ends with step 500,000, and this was the final position. Now, as I said, I have some plot scripts here. There's 2 here, plot.pot and plot.cvs. So CVS stands for collective variables, and plot.pot stands for plot the potential. I think you don't have that one. Actually, I just created it now, plot.pot, but I can show you what's inside. It just does a plot, so 3-dimensional plotting of the potential dot using some mapping, some contour plots. And if you uncomment the first 2 lines, it will actually create an image file. But otherwise, it will just use, in my case, X windows to make a plot on screen. So I open a new plot and I load it, this little plot, load plot potential, and then this is what you get, right? It's not so nice as matplotlib, but here's our little energy landscape with the black here is the minimum. There's another minimum there, and there's another minimum there, and so it just plots our potential file. So that's not so exciting. The other one is more exciting, I would say. So let's also have a look at that one. It does almost the same thing, right? It defines this contour coloring. It opens again the potential dot, but then on top of that, it opens the collective variable file and plots columns 2 and 3, which is the positions of the particle. So let's plot it. I load plot collective variables, and lo and behold, here it is. So what do we see? Well, we see again the same underlying PES, and then some green stuff here, and that are our sampled configurations. So we started, right? So remember, in our input file, we defined a starting position at 0.60. So this is where it started. And that's here. So 0.60. So it starts here. And at this low temperature of 0.5, which is very small on the scale of our energy landscape, it doesn't get anywhere. It just sits there. So it spent 500,000 steps, MD steps, just sitting in the minimum of this well, of this stable state here. So yeah, not so exciting, but that's our first result. If we do an MD simulation unbiased, it doesn't get anywhere, and that's of course the whole idea of the rare event problem. That escaping from this minimum is a rare event, and actually with those scales, even sampling this first minimum is a rare event, right? We don't get anywhere. Maybe one more plot I want to show you, and then we can think about how we can, you know, other than biasing it, how can we explore a bit more? I think that was the first question. But first I want to show you one more thing. So I'm now doing two-dimensional plots, or three-dimensional actually, so x, y, and then we have a contour plot. I also want to just plot the collective variables versus time, right? So I plot column 2 versus, column 1 versus column 2 with the line. So this is the first collective variable, which is just fluctuating up around 0.6, right? So we're here at 0.6 and we're just moving like that in 500,000 MD steps on the x-axis. And I can also plot the other one, so repeat column 3, and that one is floating around 0. It started at 0, and then actually it spends most of its time a little bit above 0, right here. So what do we see here? Well, this is just the time evolution of the collective variables, which is not so exciting here, but once we start biasing, hopefully it becomes a little bit more exciting. And it is good to also look at the time evolution. So how does it evolve, right? And especially once we start biasing, it's nice to know that it spends time here and maybe also in the product state, but we also like to know how often does it recross, how many times did it go back and forth, and then for that it's good to see the time evolution. Okay, so that was more or less exercise 1, or 0, I should say, 0 MD. Are there any questions about this part? Pretty easy, right? This was...
I have a question, Professor.
Yeah, go ahead, man.
I don't understand the temperature units in the line.
Yeah, well, have you heard about Lennard-Jones units?
Yes.
Well, it's very similar, right? So if you use Lennard-Jones units, you define everything in terms of, you know, epsilon and sigma, and it's just a rescaling of everything. Now here we don't have Lennard-Jones units because we don't have Lennard-Jones particles, but we just have a potential energy landscape that defines some scale. And so in the same sense that you can define a thermal energy, right? So you can define temperature in terms of, you know, energies, or the other way around, right? So you could say 0.6 kilocalories per mole is the thermal energy at room temperature, or 2.5 kilojoules per mole, say. So I can define temperature in terms of energies. I could say, well, in my room, it's now the temperature is is as 0.6 kcal per mole. So I do something similar here. So it's just a scaling. It's just arbitrary units, and we can make it warmer and colder by just changing that number. And instead of using kelvins or Fahrenheits or degrees Celsius, we're using a relative scale, and it's relative to the units of this potential energy landscape. Does it make any sense?
Okay. Yes. Thank you.
Yeah. I understand. Yeah, that it's quite unusual. We could multiply everything, you know, by a big number. So we could just scale this energy landscape by 600, say, and then the temperature will also multiply by 600, and then, you know, lo and behold, it's 300. But it's it's arbitrary. Okay. So, are there any other questions at this stage? Well, so then I have a question for you, which is, I have to find my tutorial. Here we are. Yeah. So the question was, okay, I lost my questions. I think the question was, what can you do other than biasing to help the sampling?
Well, you could increase the temperature, right?
Yeah, that's the obvious answer. Yes, you can just increase the temperature. How would you change the behavior system without using enhanced sampling? Yeah, yeah. The obvious, I mean, the other thing would be scale the potential file, of course. But yeah, maybe okay. I quickly try it. So here we have inputs. I'm gonna. So the temperature is now 0.5. Let's make it 10. That's quite hot. I'll run it. And done. Okay, so let's first have a look at the time evolution. So now you see much larger fluctuations. We start again in 0.6, but look at the purple line. It all the way went to minus 0.6, and at the same time, the green one, right? So the second collective variable went to 0.4. And so I think we even got some transitions now if the temperature is so high. Do I still have my other new plot? Yes, there it is. So let's also replot this one. Okay, so we had, okay, at this temperature we have crossings all the way to this intermediate state here, but we didn't manage to do crossings even all the way to the product state. Maybe if you go to even higher temperatures, that happens. And now with some fancy, you can even see how big the steps are. But mind you, I'm plotting every 100 MD steps, right? So it's not as rugged as you see here, because we're not plotting every MD step. It's probably a bit more smooth, but you can see now much bigger steps than we had before. Yeah, very good. I hope that everyone managed to play a bit with the temperature and see plots like that. Okay, then we move on to the second exercise, which is the metadynamics. Okay. I think we had to first complete the plumed file, so let's have a quick look at it. Yeah, I hope that you all managed to write something here, right? So the initial part is always unchanged. We define here the collective variables and the lower and upper wall. Then we had to add this metadynamics because we want to do a two-dimensional metadynamics. So you had to have a look in the input file. Sorry, in the manual. And finish this input file. So collective variables, functions. Oh, I'm on the wrong one. Sorry about that. Yeah, here, collective variables, functions. I should look at my local one. Yeah, so there are some inputs. There are some examples here, also with metadynamics. Oh no, we're not using PathCV yet. I only have to look at the path metadynamics, so I could have used the other one as well. So I have to look at bias, of course. So the bias, the metadynamics is here. And I'm sort of hoping that you already know about metadynamics, but if not, then yeah, you could get this from this exercise. I must say that you know, so many people have been working on metadynamics that the manual about the metadynamics has been growing and growing and growing, and there's tons of options here, which is a bit daunting, I think. But this first example catches the essence, right? So here's the metadynamics argument. You have to give, say, what is it going to be biasing? In this little example, it's going to be two distances that have labels D1 and D2. So it's a two-dimensional metadynamics, same as in our exercise. And then you have to give a sigma and a height and a pace. So sigma is, so these are the compulsory keywords, right? So you have to say, what is the width of the Gaussians? We're going to add Gaussian biasing potentials, and how often are we going to put those, what's the frequency of adding Gaussians. And you would think height is also compulsory, but since you can put options where it learns the height on the fly, it's like a tunable parameter, it's not compulsory, but here you see height is the height of the Gaussian hills. So yeah, we can also do that in our exercise, and you should have gotten something like this. The arguments are, of course, our two collective variables, right? The ones that we were printing, cv.x and cv.y. And then you also have to, since it's 2D, you have to give two sigmas, two widths. So you can have a width, a different width in the one direction as in the other direction. So the Gaussians don't have to be spherical; they can be multivariate. And a height, yeah. So what should you choose, right? I hope you thought about what is a good number here. I think in the exercise, it actually suggests some numbers. Yeah, right. So it will say, oh yeah. So reasonable widths for the Gaussians are 0.1. Do you have any idea why 0.1 would be a good number? It's based on what, right? Any idea? No. Well, I mean, so it will tell you how wide these Gaussians are, right? And of course, this is all relative to the corrugations of the free energy landscape. So the bumps and the holes that we want to fill, right? So now, first off, our landscape runs from minus 0.5 to 1.5. So the length in this direction is 3 in some units, and also in this direction it's 3. Right, so 0.5 to 2.5. So we have an idea of the order of magnitude of these collective variables, right? So they span a length of 3 in both directions. And then if we look at the holes in the bumps that we want to fill up here, yeah, they are maybe a 1/10 of this length, right? So, and one is from here to here is 1, right? So 2 of these tick marks is 1. And so if you look at the width of this well in this direction, yeah, it's about half, and in this direction is less, maybe a quarter, right? So that gives us some order of magnitude of the size of the Gaussians that we should fill, right? Of course, the Gaussian should not be much wider than the minimum that we're going to try to fill. It also should not be 1,000 of it, because then we need thousands of Gaussians to fill that thing up, right? So that's also 0.1 is probably a reasonable size to start off with. And what about the height then? Well, let's see how high should we go. Suppose we want to overcome this barrier here. Well, that's just one contour, right? Because this is dark blue and this is the next one, so it's just one contour line. Now from this plot, it's not so clear what what is the contour interval. So we can do a guess, but could be 100 maybe. So if we take a height of 1 and we put 100 Gaussians on top, we should be able to overcome this, right? Now, of course, they're not going to be all on top of each other, but so if we set 100 to 1,000 Gaussians, we should be able to escape here, I would say. So let's start off with 1. We have to start with something, and maybe it can be done much more efficient. In fact, I'm very curious to hear what settings you had, but let me just first run this one and see what happens. So we're running with 0.1. Oh, and the third parameter that you have to set is the pace. So how often should you set them? I chose 500 here. Yeah. What is a good number, right? I wrote a paper about it called A Recipe to do multidimensional free energy exploration, or something like that. And yeah, I don't go into details now, but if you want to read more about how to choose these parameters, then I can recommend you that paper. which I discussed in the first session. Okay, so now we created one extra output file. We already talked about callvar.out, which just shows you the directory of the collector variables and time. The output, which is not so exciting unless something goes terribly wrong, then you can look for errors there. And now we have this third file called hills. So the hills file is created by the Metadynamics directive. And it has the information about where are these Gaussians placed and what is the shape of these Gaussians. So let's have a quick look at them. And so we can see if we can understand. Again, there's a header file and it tells us what is there. So the first column is the time. So you see here every 500 MD steps it puts a Gaussian. Each line is a Gaussian. And we asked a pace of 500, and that's what you see here. 500, 1000, 1500, 2000, right? So the first Gaussian is put at 500 MD steps. At position, CVX, CVY, right? So this is the position. So the first Gaussian is actually close to the minimum, because remember, we start at 0.60, and in fact, 0.61, 0.05. So that's the initial position of the first Gaussian. And then sigma in the X direction and sigma in the Y direction. So these are the widths, which are in fact 0.1 and 0.1, as we said. There's the height is 1. And then there's a bias factor, which, you can look up what it means, but it's not relevant for this exercise. Right, so it puts many Gaussians. And now, can we look at the free energy landscape? Well, to see, so, the sum of these Gaussians, if you run long enough, is an estimator of the underlying free energy landscape. So we just have to add up all these Gaussians, and we're not going to do that by hand. We're using a tool that is also built into PLUMED called SumHills. And I hope you all got it to work. I put it actually in my run.me script, so that I don't want to do this every time by hand. So I run PLUMED, but now not with PSMD, but with SumHills. And I tell it to read the hills file, and it will produce an output file. And this thing is not so important. Min to 0 means that the minimum is going to be 0. And it produced an output file, fes.dat, and we can plot it with our little script plot underscore fes. So let's do that. So do I still have Blueplot open? No. Okay, so first let's start with looking at the dynamics of the collector variables, right? So what happened with the collector variables? So I'm plotting again the collector variables as a function of time. So 1 against 2 is the first one. And this is looking very promising. So if you get something like this, then that's a good sign, because the first collector variable was placed at 0.6, right? And what we see here is fluctuations that get bigger and bigger and bigger. So what's happening is that these Gaussians are placed in the minimum, and it pushes the dynamics out away from the minimum, and the fluctuations from one end to the other end get bigger and bigger and bigger until it escapes here. And now it can also reach this intermediate state, which was somewhere close to 0.5. And again, we see very large fluctuations getting larger and larger and larger. And sometimes it spends some time in this intermediate, and sometimes it spends some time adding more layers in the initial minimum, right? And then after about, 18,200 or so steps. No, what is it? It's even more, right? It's 180,000 steps. It overcomes the bottleneck, and this is probably the product state, and then here it goes back. So let's also plot the other one. This is the other collector variable, which starts at 0, fills in the first the reactance state and the first intermediate, and then it goes here to the product state. So this is looking nice. So we have one crossing to the product state, and we have here one recrossing. So now it's back in the product state, reactance state, after more than 450,000 steps. And then here it goes back and forth, back and forth, back and forth, because stuff is more or less flat now. Now I can also plot 2 against 3. So now we see our dynamics in 2D, right? That looks like this. Oh, that's not good. This, no, what's happening? Okay, not sure why this not works. Oh, wait, I should not do that. I should do plot. So plot, right? Let's do it with lines, or lines and points. With lines in. Oh, 23 lines and points. Yeah. Okay. So this is what it looks if we just plot the collective variable 2 versus 3. Right? So we start somewhere here, and the dynamics went to the intermediate state, goes back and forth, back and forth. Here it crossed and fills the product state. But it's more fun to look at it on top of this landscape, this PES, which we can also do with plot f CVS. So let's do that. New plot, load this plotting program, plotting script. And then it looks like this. Okay, so I hope you all managed to get something like this. So clearly our metadynamics simulation was not long enough to explore the whole landscape here, right? So all this part here, which is very high energy, we didn't go. We just filled in the interesting part, the reactant state, intermediate state, and we crossed a couple of times in product state, right? So not bad. And this is also, yeah, I think one of the reasons why metadynamics is so efficient is that, and why can you afford to do 2 or even 3 collective variables in metadynamics, is because it focuses the sampling on the low energy parts. Of course, I can keep on going, and then eventually we'll explore these parts as well. But if you would have done, let's say, good old-fashioned 2-dimensional umbrella sampling, then yeah, you would have probably put a grid here, a 2D grid, and put windows everywhere. And then of course you sample the whole space and also all this part, which is not so interesting. So that makes it much more expensive. Instead, now it's still an exponential scaling with the number of collective variables, but the prefactor is much better because yeah, we only spend time in the interesting parts. Now, what more can I say about this? Of course, we would like to know if we converge, right? So how would you know if we're done, if we are converged? Have we sampled enough? Do we trust our free energy landscape? Any ideas about that? What can we do? Did anyone think about that or have some ideas about it? I'll take that as a no. So yeah, so what you can do is, there's many things you can do, but you can, for example, so often we are interested in not in the whole free energy landscape, but for example, relative free energies, right? So the free energy difference between the minimum and the maximum, the reactant minimum and the product minimum, for example, or the height of the barrier with respect to the reactant state. And that difference, of course, we can probe, right? We can just calculate what is maybe also with some hills or otherwise by hand, just sum up the hills at this point, 0.60, for example, and let's say the top of the barrier, and then see how that change, that energy difference evolves in time. We can just plot this function of time. Now, so even though we keep on adding layers of Gaussians and etc., right? That difference should at some point converge. So initially, we have no idea. The difference is 0 because we haven't been here and here. Then it will become maybe a big number if we only fill this part. But once we've filled everything, and then we're going back and forth, that difference should become reasonably stable with every extra layer of Gaussians that we put on, and we can take a running average, for example, over the last part of the simulation once we've filled once it's fluctuating around some average. And of course, you can do that for every point, right? I can take any difference, so I can, and so we can just we can do a running average. Another way of doing it, a little bit more sophisticated way, is using a method that will just converge the Gaussians, right? So use one of these adaptive, metadynamics methods. For example, as we discussed last week, the well-tempered metadynamics, right? So that one will adapt the height for you on the fly. There's only one hyperparameter, which is the bias temperature. So until how high would you like to fill up? To what energies would you like to fill up? And then it will just make the Gaussian smaller and smaller and smaller and converge. But then, okay, yeah. So I hope that's a bit clear. Any other questions about exercise, the metadynamics exercise number 2?
I have a question.
Yeah.
If we don't know the potential, how we can correctly choose sigma and height of the Gaussian?
Yeah. So I don't hear you very well, but I think you asked me if you don't know the underlying Ferenczi or underlying Ferenczi landscape or the potential energy, which is almost always the case, I would say, because if you already know the answer, then you don't have to do this exercise. So usually we don't know it, of course. And then how do you choose these the height of the Gaussians, for example? And the answer is unfortunately, you don't. You have to guess. But usually, we are chemists or biochemists or physicists, and we know a little bit about that problem, and so we have an estimation of these numbers. What should be the order, right? Now, the way metadynamics works is it puts a Gaussian somewhere, a repulsive potential, to push you away from that part, right? To encourage you to start exploring other places than this minimum. But if this minimum is deep, then you still don't escape, and you have to add more Gaussians, right? But now the thing is that so once you've put a Gaussian, the system needs a little bit of time to fall off that Gaussian and find now a new minimum, right? Maybe next to that Gaussian. So you have to wait a little bit and then put another Gaussian. And then you wait again a little bit and you have to put the Gaussian. So you also need to know something about the diffusivity, because maybe it takes a long time if the system has a slow diffusivity. And so it's possible that you put Gaussians in the wrong places because maybe you didn't wait long enough, or maybe at some point it was already flat, but then you still put a few more Gaussians, so now there's some bumps. And the way metadynamics works is that it's in a sense self-correcting, and this is especially important when you do path metadynamics, when we are not only trying to estimate the free energy with Gaussians, but we're also estimating a reaction path using an adaptive path. And so we're adding a bias, but on a path which is still moving, which still hasn't converged maybe to the free energy. And so maybe we really put Gaussians in the wrong spots, because we're putting Gaussians on a path which is still moving. And then this self-correction is really important, because maybe we put Gaussians in the wrong place, and then after the path is converged, we can really settle and fix all these problems with extra layers of Gaussians. And why am I telling you all this? It's because if the Gaussians are much larger than the thermal energy, so at room temperature, the thermal energy is about 0.6 kilocalories per mole, or 2.5 kilojoules per mole. So if you make the Gaussians much larger, then it needs more than, it cannot overcome anymore that. You really need a whole layer of Gaussians to be overcome the first Gaussian that you put in, maybe in a wrong spot, right? Instead, if it's in the order of a thermal energy, you can still overcome that one because, well, it can overcome bumps in the landscape that are in the order of the thermal energies. So no matter how high the barriers are that you want to overcome, or how deep the wells are that you want to escape from, I don't recommend to use Gaussian heights that are higher than thermal energy. So larger than 0.6 kcal per mole, I would not recommend. Maybe use half or so, right? So it's still easy to repair if you put Gaussians in the wrong spot. It's much easier to play with the pace. How often do you put them? And that depends on the diffusivity as well. And I mean, they are very much related. So the height of the Gaussians and how often you put them, they're related. So either you make them bigger or you put them more often. So even though maybe, if there's a problem where you have very high barrier, you may think, okay, now I'm going to put really big Gaussians because otherwise it takes forever. But yeah, you're still going to pay a price. So you can do it, but make sure that at least after having escaped and having come back, you start to use smaller and smaller Gaussians to get a reasonable accuracy of free energy differences. But it's hard to guess in advance. Yes, I understand. It depends on your problem. It depends on many factors. And again, I recommend you to read that paper that I mentioned in the last week. And it's also in the slides that I put online called The Recipe. And there's also this paper of Alessandro Laio and co-workers that I referred to called Assessment of Metadynamics, with some really good hints on how to choose the parameters. More questions?
Yes, like how would you estimate the CV diffusivity?
Diffusivity, how fast it diffuses. Yeah, usually you get that sort of information. And when I mean that sort of information, I mean also an idea of, for example, the widths that you should use from the initial simulations in stable states. It's always a good idea when you set up your system to equilibrate it a little bit. Right, so often you would run first in an unbiased simulation in the reactant state, and usually also in the product state, but at least in the reactant state. And that gives you some idea of, well, the size of the fluctuations in the reactant state. So you already have some idea of how wide is the... And that also tells you already something about the diffusivity. So how long does it take to go back and forth and explore in one collective variable? So I always recommend to do an equilibration and already switch on Plume and plot some collective variables. You can always do it then afterwards as well with the Plume driver. So if you forgot about plotting some collective variables, just read your equilibration simulation trajectory with the Plume driver and plot some collective variables, and then you get some idea on how slow does it move, how long does it take to move back and forth. That gives you some idea of diffusivity.
Yeah, okay, thank you.
Okay, then exercise number 3. And we're going to first run with a fixed path. Okay, I think I already put numbers here, so I sort of forgot what in the original exercise, if there's already numbers here or if you have to put them. But now we have 2 directives here, on top of this stuff that we always have that we can sort of ignore, this header stuff. And one is the path collective variable and one is the metadynamics, right? And then we have a few extra things that I can discuss as well. So we're doing metadynamics, and I used a slightly different syntax to make things a little bit more organized. Maybe you know this sort of syntax. If you type the main keyword with 3 dots, then you can put all the arguments below each other, and then you have to end again with the 3 dots and metad, which is nice if you have many keywords to set and you want to keep it readable. So that's what I did here for the metadynamics. And I give it a label. Usually we put the label in front with a colon, and then we put the first keyword with all the arguments. Here, with this syntax, you have to use the label keyword to give it a label. And these labels are important because, we use them for printing, right? So, for example, if I want to print the bias, for example, in a call var out file, then I use these keywords. So I always put these labels. So I put the label here.
Can I say something?
Yes.
I don't think you have to put this label equals whatever. You can also do it in front of the method, like with the lower walls and whatever.
But also, if you use the 3 dots.
Yes.
Oh, okay. I didn't know that actually. I could have done that as well.
I think so, but I may be wrong.
Yeah. Okay. I was not sure of that. So thanks for this input. I know there's some redundancy, and you can do things in different ways. It's a matter of taste, and here's my taste. Now for the argument. So now we're moving from, instead of doing a 2-dimensional metadynamics on this little landscape, we're gonna do it on a path, right? On a path collector variable. And so we're gonna bias the path, and the path actually has 2 arguments, 2 components, a little bit like the distance, right? So we had a distance where we can put components, and we have an X component and a Y component. Also, this path, which is defined here, has components. So the name of the path is actually, so the label is path PCV, and then there's 2 arguments, 2 components, an S and a Z. And maybe I'll quickly show you how this is also found in the documentation. So path CV, we're here, and so here's the description of the components. And so we have an S, and the other one is a Z, and the S gives us the position on the path. And so what does it mean, a position on the path? Well, that if we have some path, some straight line, for example, that goes from the React state to the product state, then if we are going around somewhere, we're doing a dynamics and we're moving somewhere here, then each point will be projected using the shortest Euclidean distance to the path, and we want to know that position, and that position is S, and it's going to be a number between 0 and 1, right? So we have a fixed point here, then we have a number of points in between, and then the final fixed point in the product state, and so so we're moving from 0 to 1, and we have this projection, and we want to know where is this position. So no matter where we are, we can always project on that path. But then we also would like to know how far we are away from that path, if we are somewhere in this space. And this is Z. So Z is the distance to the path, and S is the projection between 0 and 1. I'm saying we're always between 0 and 1. That's not completely true. We can also add some trailing nodes. So we can, before the first fixed node and after the last fixed node, we can add so-called trailing nodes, and then we can also go get numbers that are smaller than 0 and numbers that are a little bit larger than 1. And maybe at this stage it still sounds a bit abstract, but it becomes immediately clear if I show you the example. The rest is more or less the same, except that now we have only 1 sigma because we're moving in a 1D bias, right? So instead of 2 sigmas, I have only 1. You could ask yourself if 0.1 is still a good number, right? But mind you, before I was talking about what is the span of these collective variables, which was 3, and the width of a hill of a well is in the order of 0.5 or so, and so I argued that the order should be somewhat less, like maybe an order smaller than those numbers, and so we end up with 0.1. Now we're going to move along a path. We're putting Gaussians on a path that runs from 0 to 1. So we span 1, and on that scale, this is again probably a tenth or so, right? So again, it's more or less the same order. maybe we should make it a little bit smaller, but let's see how this works. You know, maybe 0.1 is a bit too big, but I think it's reasonable. The height, we could have chosen the same thing. I chose here 0.8, so it's actually a bit smaller, but also, you know, that should not change. I think we can still use the same height, and we can also still use the same pace. Now let's have a look at the other directive. So here we define our path collector variable, right? So we have a path collector variable, which has a name, and it takes as the arguments the two collector variables. So it's going to be a function of these two collector variables, right? Now we have to start from an initial path, and there's two ways of getting initial path. Either you read one from a file that you can make by hand, or you made another way using Plume driver, for example, or you can also have it generate a path with this keyword genPath. And then what it will do is just make a straight linear interpolation between 2 points that are fixed. And the idea is typically that you use as fixed point the minima of the stable states. That it doesn't have to be, but well, at least in this exercise, that's what we do. And yeah, that's you know, how it's meant to be used, but then maybe you can think of the other applications where you don't do that. Now, the first three numbers in this genPath are the number of nodes before, in the middle, and after these fixed nodes. So 20 means, okay, we have 20 nodes in the middle between 0 and 1, between fixed nodes, and then we also have 20 trailing nodes in front and 20 trailing nodes at the end. You don't need those in principle. You can set them to 0 if you want. Sometimes it's nice. And the reason I must say I like it personally, but that's just because, yeah, if you want to get a free energy landscape between two fixed points, it's nice to afterwards also see if these minima were minima, or that maybe the minima maybe still, you know, going a bit down, and maybe your fixed points were not optimal, and well. And secondly, yeah, if you really want to correctly calculate energy differences between the minima or the minimum and the barrier, yeah, you should integrate over the minimum, right? You should in principle also get the entropy along, the entropic contribution along the free energy in this minimum. And so if you want to do that, you need that end where it goes up again. And so it's nice to have some trailing nodes to also see that, yeah, if you move beyond the minimum, the free energy goes up again. Okay, and then what are these numbers here? There's 4 more numbers. Well, the first two define the reactance state, right? That's 0.60. It's also our starting point of the MD. And the other point, minus 0.5, 1.5, defines the minimum in the product state. So this defines our initial path. Node 21 and node 40 are fixed, and we're not updating the path. Right, so the pace is 0. We will never update it. We will also never print it. Stride is how often we print it, 500,000 steps, so that's not going to happen. And I'm not going to say anything about this half-life at the moment, but we'll get back to that in the last exercise. And then it prints the path to an output file. Okay, I hope that's a little bit clear. Then if you run it, it will create now yet again one more extra output file. Right, so we already had the callvar file, we had the output file, we already talked about the hills file, and now there's an extra file called path.out. Now, let's have a look at what it looks like. Lots of numbers, lots and lots of numbers. Now, let me explain what it says here. Of course, first we have a header. That's always nice from Plume. It tells you what's inside. And the first header tells you the step, the time, the number of collector variables, and the number of nodes. So the path is defined as number of nodes, right? So we have 20 plus 20 plus 20 is 60 nodes. That's what you see here. We have two collector variables. It's a function of two collector variables that's set here. And then this is step 500,000 and time 500,000, because we asked to print only once at the end, and that's what you see here. And then what does it print? Well, these are all the nodes of the path, right? So there should be 60 lines here, and this defines each path node, which is defined spelled out here in this second header line. So this is the node number, node 0, 1, 2, 3, 4, all the way down to 60. This is the position of the nodes in this collective variable space, CVX and CVY, right? So, and let's check if the first node that is fixed, which was node number 20, is at this position that we thought it should be, which is 0.60. And if we go to node number 20, the fixed node, you see, in fact, yeah, it's at 0.60, right? And these are before, these are after. In a minute, we will plot them, and then it becomes completely clear. Now, what are all these numbers behind here? They're not so interesting for us, but they are interesting for the program if we want to restart. So it uses it to restart it. So what are these numbers? I can quickly tell you. It says here Z average CVX, Z average CVY. So what does it mean? Well, I already told you Z is the distance from the path, right? So how far are we from the path? And then average, so it's the average Z over 500,000 steps in the X direction and the Y direction. So basically what it does is you have a fixed path and there's all these nodes, and what the path CV implementation keeps track of is that when you do dynamics along this path, it keeps track how far do you pass each node. So every time you pass a path, for example, suppose you are in between two nodes, right, and you pass on the left, it will calculate the distance to the closest two nodes, and it will divide, it will keep track of that distance, right, and it will divide it over these two closest nodes. So if you're very close to the first node, then it will count most for that closest node and only a little bit for the other one. But if you're in the middle, and it's, yeah, it will, they both get a weight of 0.5, and it keeps track of that distance, and during the whole MD simulation it will add up that distance, and it will get the average weighted, and the total weight is given as the last column. And so why does it use this information? Well, if you do an adaptive path, so you want to now update the path, then it uses that information to move the nodes, right? So it just calculates what is the average distance in this CV space, weighted. It will divide this number here. So here, for example, it says 63. It will divide it by the weight, right? And that's the distance it has to move. And then it will move the node there and start, keeps on adding. So that's how it calculates the update of the node. So it's basically a measurement of the density, the visited density, the flux. So a very simple algorithm. Okay, that's just technicalities. Let's look at the plots. That's probably much more exciting. And instead of plotting it, I will just show you the results from that I already prepared in advance. This we discussed. And here I zoom in a little bit. I already showed you this. No, I didn't show you this either. Okay, I will start with this plot then. So here's the results of our fixed path. So the fixed path here is shown as the purple line. You don't see the 20 nodes, or actually 20 plus 20 plus 20, so 60 nodes, because I'm just plotting a line here. But the crosses are the fixed nodes, okay? And then there's many nodes in between, and they're not being updated in the simulation. But it's enough, even though we bias along this projection here, along this path, that's enough to push it out of this minimum here along the free energy landscape. And so so the dynamics, even though it's pushed along the direction of the purple line by adding Gaussians on the purple line on the path, the dynamic still follows the underlying free energy landscape. Right, so that's nice. So even if the path is not perfect, if the well is if the path is deep enough, it will follow the path through the free energy landscape. So that's kind of nice. We can look at the S variable, the progress variable as a function of time. So this is 500. I wrote here picoseconds, but okay. I should have written arbitrary units. But yeah, you see it starts at 0. So 0 is the product reactant state, 1 is the product state. And you see that, again, the dynamics is looking good. I always like to see this slowly increasing fluctuations, right? Fluctuations get larger and larger, and then here it manages to escape, and then now we are in this intermediate state. It goes back a couple of times, and then finally the whole this whole first well has been filled and we escape to the product state. And then here we escape back. So this is the first recrossing. And then we go back and forth, back and forth, back and forth. I mean, the dynamics, if you have seen many of these plots, if you've worked with this a lot, you see that, yeah, this is not looking so healthy. Not what I'd like to see. For example, here you see the opposite behavior of what I like to see, where you start with small fluctuations that get larger and larger and larger. You see something weird. And also sometimes it looks like it gets stuck for a little bit, like here. And that has to do, of course, with the fact that, yeah, this path is not a good path, right? So we're biasing sort of in the right direction, but for example, to escape from this product state, we have to move almost orthogonal to the direction that we're biasing, right? So this well runs in this direction, which is really orthogonal. So the bias is not helping to escape back from the product state, right? So this is, of course, not a good path, and we should adapt the path. Anyways, but that was just a fun exercise. There's one more thing I want to show you, which is this dynamics. So how did I do this dynamics? Now you see that the dynamics, the green spots that we sampled, is really very close to the path, right? And how did I do that? Well, I used this extra potential that I skipped over. So here's again our input file, and there's this extra line here called tube. It's just a restraint that works on the Z direction, the Z component of the path, the distance of the path. And so it's a harmonic potential fixed at Z equals 0. So that's, you know, 0 distance from the path, there the potential is 0, and then it's a parabola on the distance of the path with a pretty steep force constant of kappa over 1000. And so it really tries to keep the dynamics close to the path, and that's why we call it the tube potential, because it functions like a tube around the path, right? So if you use that, then you get this second example where now we're really sampling close to the path. Maybe we've kind of done even a little bit closer, and so what you then get is really a slice of the free energy, right? So we're slicing here through the free energy landscape. So we have a two-dimensional free energy landscape, and here's a slice through it. So this is dynamics, and we can also look at the free energy along this path, right? So we can use the sum hills and get sum over the hills of this, and then you get this plot, right? So this is now a slice along the path, which is not really relevant from, you know, chemical point of view, because who cares? It will never follow this path really. But if, in case you're interested in taking a slice through a free energy landscape, then this is something you could do. Okay, so this is the reactance minimum. Here's our little intermediate. This is the top of the barrier, the transition state, and then we fall here in the product state. And this is then the part of the trailing nodes, right? So I said that, yeah, sometimes it's nice to also see how fast it goes up again. And in case you really want to integrate over this well with respect to, let's say, this well here, then yeah, you need this part actually. So it's nice to have some trailing nodes there. Does that make any sense so far? Yes. Are there any questions over on this part with a fixed path? No. Okay, I see Bas saying no. Very good. Thank you. I think this is all I wanted to say. Maybe there's one more thing I would like to say, because in 1D, actually it's not so difficult to show the convergence of the free energy. It's easier in 1D. So I have here my hills file, right? So this is the hills file. It put 500,000 hills or so. Now, you know, the position is only 1D, so it's only one column. The width is also only one column. This is the height, 0.8. And I can use again this sum hills to plot it. But I can do that with a stride, which means I can plot every so many hills. So let me run this command one more time. Right, and so what it did now is it created many FES free energy landscapes with a stride of 10. So every 10 Gaussians it will it produces a frequency estimator. And so let's plot them. So here's the first one, FES 0. So this is the first few Gaussians. Mind you, the Gaussian height was 0.8. And I think this is the first 10 Gaussians. And it looks like they're really perfectly on top of each other, because look at the scale here on the y-axis, it's 8 actually. So these are 8 Gaussians pretty much on top of each other. Right? So it clearly could not escape anywhere. So it's a nice and smooth Gaussian. You can add a second one. So this is FES number 1. So 16, right? So we're really building a mountain here. Okay, now let's go a bit faster. I go to 10. Now we already see a little shoulder happening here, right? So this is 60 energy units. Okay, I go to, 20. More shoulder. Now, okay, let me go quickly out. And do I still have my other plot here? No, okay. The new plot, I want to show you again also the, what do I want to say? Call file? No, I show you the hills file, but then as function of time, right? So mind you, I can just plot this as a function of time, because my first column here is the time, right? So after 500 steps, I put the first Gaussian at this position with this width and height, and I can just plot that as a function of time. So I plot hills, column 1 and 2, 1 and 2, right? Okay, so let's have a look at these two together. So here we see the Gaussians being placed, right? Here, I'm interested in this point here. So let me move this up a little bit. Here we have the first escape to the product state at, let's say, 17,000, and I should divide by 500. So if I do it slightly different, so this is after 350 MD steps. So let me put here now. Okay, back to the other one. Foreground number 1. So I want to plot number 35, right? And so here we are now escaping to the product side, and now you see the first little bump here at the product side at 1, right? And so we can see it going. And then now let me show also the other one. Here we're going back at 600, right? So at 600. We're going back, so 60. And now you see the blue line here. We filled the product state, and here we're going back. And so we've added, with respect to the yellow line, a few here, and we're back in the reactant state, right? And so from here on, now we're going to just add layers and layers and layers. So it took 60 Gaussians out of the 100 to go back and forth. And now we're just, we can see how it, okay, let me put also 70. See, it's just the same thing, just shifted down a little bit everywhere. 80, another layer, right? So it just goes back and forth. I go 90, and here we have, okay, and then the last one is probably 100 or 99. Let me see. Can I still have a 100 here? Yes. Okay, so do you see how after 60, can I make this thing bigger? Yeah. I'm just adding layers here, but the energy difference, right, between 0 and 1, say, or between 0 and, well, what is my product state? 0.7 is not going to change much, and I can just take a running average over this difference, and so you can see how it converges. Now, if you don't have a good converged path, or if you don't have a good set of collective variables in metadynamics, say, you will not see this behavior. You will see a hysteresis. It will fill first the reactant state, then the product state, and the reactor state, and right. So you really would like to see this evolution of the free energy landscape. It should be a nice smooth lowering of the but if you see it fill up and undo what you did before, right? So maybe fill this part now up and etc. Then okay, there's something wrong with your collector variables, and you should go back to the drawing board and see what are the missing collector variables. This is very important for any biasing method, right? Not just metadynamics, because with metadynamics this is how you see that, but also with other biasing methods you should always worry about, do I have a good set of collector variables? Okay, I hope I'm not telling you new things, but well, okay. So final exercise, or at least the final thing that I want to discuss. I don't want to talk too much about the multiple Walker part. Although, yeah, there were some problems with that, so of course I will address those. Yeah, we're going to the last exercise, which is now we want to optimize the path. So maybe I first show again the input file. So quit, and I go to adaptive path metadynamics. I show you the print file, the print input file. And yeah, so if you just yeah, looked at the input file, actually the numbers set there were the same as for the fixed path, and you were supposed to change those numbers, right? So the numbers that you had to change was pace, stride, and maybe this half-life. So what are good numbers to set for the pace? Well, it's a good idea to balance that a little bit with how often you update the metadynamics biasing potential, right? So you could even say, well, let's use the same numbers. So the metadynamics pace is 500, so every 500 MD steps set a Gaussian, and maybe that's not a bad idea to put the update of the path with the same pace. So you could put 500. You can also make it a bit slower. You could say, well, can put a couple of Gaussians before I update the path. But it's dependent on the problem, and I very much recommend you to play with it a little bit. But yeah, putting a pace of 500 or 1000 is probably a good number. It makes sense to put the stride the same number, so every time you update the path, you also print it and you can look at it. But if you want, you can make it much slower, right? So if you do many updates, maybe you don't want to see all of them, and maybe you get very big files, and you make the stride a little bit lower. Now then, finally, what is this half-life? This half-life sounds weird, right? And the idea is as follows. As I said, these last three columns in the output file, the path output file, are the average distance from the path with a weight factor that tells the program where to move those nodes. And that's kept being updated, right? And so even if you move the nodes back to 0, now that's the new average, it will keep measuring distances and add those, and the weight will be keep increasing, right? And so if you don't have a half-life, then these weights get bigger and bigger and bigger, and every new information that you add, so every new measurement of a distance, the next time you pass a node on the left or on the right of your path, will count less and less and less, because maybe you already passed 1,000 times, right? And of course that's fine, because things should converge. But convergence can be very slow, especially if the initial guess path was a pretty bad guess. Because then initially these distances were very big, because maybe you had to pull the path far away from this bad guess to where the free energy landscape wants to push you. And so and that may really bias the running average. So you will have a bad start for your running average, and it will be good to forget about it. So that's what this half-life does. This half-life makes the running average forget about data that was a long time before sampled, right? So if you set it to 1000, for example, it means that so measurements of the distance of 1,000 updates ago or 1,000 MD steps ago will only count for half. That's what it means, half-life. And after 2,000 steps, it will only count for a quarter, and after 4,000 steps, etc. Right? So that's what it means, half-life. And so, especially if you have a bad guess, it makes good to use a small half-life, so it will quickly, move the path, and forget about this initial bad guess and these large distances that it sampled, until you fall into the free energy landscape path, and then you want to converge, and then at some point it's actually good to have a larger half-life. Okay, so that's, but I recommend you to use a reasonably small number, maybe in the same order of the pace, right? Like 500 or 1,000 or something like this. So that about the input file. Now about the results. So here's a reasonable example. Right, so I set the pace to 500, and then I put the stride also to 500, and the half-life is here 2,000. Right, so more or less the same order, like 4 times bigger or so. The rest is the same. Right, so the metadynamics is again the same. Well, the height is now 1 instead of 0.8, but fine. And we're running initially without a tube potential, right? So there is actually a tube potential. You can set it to 0 if you want, or not. You don't. So without a tube potential, it will actually move faster. In the limit of having a very tube potential, it cannot go very far away from the path, right? So, and then in the limit of having it very steep, so it stays very close to the path. Actually, what it does is basically following a steepest descent along a gradient, right? So it will really fall into the minimum free energy rather than taking the average path. But okay, that's a technicality, and I can talk more about it if you want to know more about it. But in any case, this is one example that you got. It's not well converged, but it's just, so with those settings and running not too long is what you get. And you get a pretty reasonable path, actually. It follows this funny S shape here, going through this intermediate state, this little minimum that is about here, and takes this corner, and then it goes here to the product state. In this run, actually, we took out the trailing nodes. Is that true, what I'm saying? Let's have a look here. Yeah, so we use this gen path 0, 20, 0, right? So there's no trailing nodes, which is, just a choice. You can also leave them there. And then this is the dynamics going back and forth, which is pretty efficient, right? It escapes quickly back and forth, and the final free energy landscape. And then, you can do the same analysis, right? You can plot the evolution of the free energy landscape and things like this. And also, sometimes something that I personally recommend is I often start with reasonably large Gaussians and a fast pace and a short half-life, and just fill the reactant state and the product state, and then I stop the simulation and I do a restart. And how do we do a restart? Well, in the Plume file, you type restart, right? That's written in the manual. And then the Gaussians, it will read the Hills file and continue with those Gaussians. And you can also give it now an input file. And all you need to do is take the last frame from your Hills, from your path file. And maybe this is something that I should show you for a moment. So we have now a path output file. Okay, maybe I should run this for a moment. I see that I don't have it yet. Oh, I didn't even make it executable. +X. So I run it. Takes 1 minute. And also, and also because I would like you to show this animation, because maybe you've seen these anim files. These are little animations that you can do with NuPlot. And of course, you can also do it with Matplotlib if you want in Jupyter, but they're fun to watch. So we'll wait 1 moment. And what I wanted to show you is that now the path output file. Oops. Okay. Which is here, path.out, has updates of the path, right? So, oh, brilliant. I didn't update my input file. I should have done that. Okay, so let me update this. I take a pace of 500. I take a stride of 500. I take a half-life of 2000. And I also keep the trailing nodes. Why not? I'm happy with my height and width and pace. Shall we do it with this tube? Why not? Here we go. One more time. And so, yeah. So the point is that you can watch these updates of the path file. Of course, you can cut it out and then plot it. But with some GNU plot directives, you can also just choose which block which you plot. And, this is what I want to show you. And I also want to show you that you can take out the last one, the last file, the last 60 lines plus header, and use that to restart. So this is what I want to show. So now it's done. You watch in the path file. And now, okay, so I said, pace and stride is 500, so every 500 does an update of the path. And so here's the first one, right? So the time is 500. Now, mind you that, so look, this is now all 0, except here, right? So this is node number 20, which is the fixed node at 0.6 and 0. Can you see this, or should I zoom in? Is it visible? Is it okay? I can make it bigger, eh?
Yes, I can see.
Yeah? Okay, thanks. I'll make it a little bit bigger, but thanks for your feedback. Yeah. So it has only sampled here and here, clearly, right? Now, why are these 0? Because clearly the weight is not 0. That is because this node is allowed to move, and so it actually did an update. So now the average is set back to 0. So these nodes have already, this node has already moved a little bit. This node cannot move, it's fixed. And so that distance remains standing there. It just reset the weight. The weight is 0. It doesn't do anything with this number. Instead, this one, it actually moved the node. So the measured width is now set to 0 because it shifted the average. And the weight is kept for, further increments. Okay, so that's the first frame. Then the next one is here, 1000. Etc. Now I just moved to the last one. If you cut out this one, so this is now the last one, I can use this to restart, right? So I just throw out everything before. I call this thing, path.in or path.restart. And then instead of using the gen path directive, I use infile and give it, and then it will continue from here, right? So it will read those the new path and etc. Now let's also look at this animation. So new plot, and I load my animation. There's 2 of them. Let's first have a look at CVS. So how does these collector variables and the path move? I'm not sure how fast this goes, so pay attention. I will run it a couple of times otherwise. And then we look at the update of the frequency landscape, okay? So here's the anim CVS. Of course, you can also run this yourself, right? So here we go. Now the green dots that you see is where we are running right now, and it shows, so is there a time running? Yeah, so on top you see the time. It runs to 500, right? So we're halfway now. And it's, 250 only, sorry. And it shows, I think 5 dots, 1, 2, 3, 4, 5, 6 dots. So there's 1 dot and then a few dots before and a few dots after this time. And actually it's running like a crazy. It's pushing a lot, clearly. And then you see also the update of the path. I will run it again. So initially it's here, and you see the path only updating here. And now, so you see the, it went a bit crazy. I think I saw it even go all the way up here. So maybe the Gaussians are a bit too big. So, yeah. Now, one thing disadvantage of updating the path a lot is a technicality that is has to do with the reparameterization of the path, and it works as follows. If I move the path, so if I've sampled close to some nodes, I want to move those nodes out. But in order to calculate where I am between 0 and 1 and do this projection, it's important that these nodes are equidistant. So I have 20 nodes and they should remain equidistant. But if in the beginning I move a few nodes away, so the distance between the nodes becomes larger, I have to reparameterize all those nodes and move them all a little bit, reparameterize them along the string to keep them equidistant. Now that's all fine, except that the algorithm that is used is maybe a little bit too simple algorithm, in the sense that it tends to cut corners. So what that means is, if I'm going from here to here, now I sample in this direction, and every time I re-optimize the path, you will see that this path tends again to become more straight again. It's undoing the work that I did before. And we thought about this a long time because we didn't like that behavior, and we came up with smarter algorithms, like, for example, using splines and things like this. But the problem is that, well, also that has disadvantages. So this is a little disadvantage, that it cuts a little bit corners. You can try to avoid that, but then, yeah, there's other disadvantages, I think. And in the end, yeah, we don't mind so much. And especially if you use the multiple Walker version and you sample at the same time here and there, then this problem is gone, actually. So we really like the multiple Walker implementation in practice. And the other thing is that, yeah, often this problem only appears in the beginning, when you still have to wait a little bit on one side to fill it before it can go back. But once everything is filled and can just go sample back and forth all the time, then this corner cutting is not a problem anymore, because you're sampling all the time along the whole string. Okay, one more time this movie. If you have any questions, then let me know. You see that now this becomes a straight line again. It was already an S, but now it's sampling on this side, and it has completely cutted all the corners here. And we have to wait for it to go back, and now it recovers again the S, but now it starts to cut a bit the corner there. But now it has seen all the parts, and it will just go back and forth, and then it will converge. If you now keep on going with smaller Gaussians, it will become very smooth thing. I hope you played with this a little bit, and maybe also try the restart, and then yeah, got an even more smooth result. This is still, quite ugly, I would say. Yeah, I also wanted to show you the other one. So loads unfes. I should probably reset because I'm setting. Yeah. Okay. So here we go. Oh, that was too quick. Oh, I should put in a sleep or something. Okay, there's no hope you can see this, people. Okay, don't blink because this goes super quick. I'm not sure if I can fix this. Yeah, okay, this is too quick. No, okay. Can I do anything about it? I tried to fix it, and okay, here, if I set this to 1, it's 10 times slower, right? Let's try this. Still pretty quick. Okay, it's a bit slower now, but you can see it starts here, it crosses, now it does the product state, and then goes back, forward, back, forward, back, forward. It's more useful just to plot with the strides, and then you see the, yeah, okay, I'm sorry about that. Anyways, okay, I hope this is a little bit clear. If there's any questions, please speak up. I see I'm already talking for 2 hours. I really thought would be a short session, but no questions? Okay, then I want to end with showing you a little bit about the multiple Walker stuff. And the way, I'll just tell you how it works, basically. So what I do now is, again, I have my run me script, but what I do now is I start 2 plumes at the same time, or more. You can use more walkers, but in this case I just use 2 walkers. And the reason is, this is so super fast that if I think that if I run more at the same time, I will have conflicts, because the way the communication goes at the moment is through reading files, which is of course a rather stupid way of communicating between things. Now, in practice, that works like a charm, because yeah, we're not updating so often either the hills or the path, so it works fine. Because MD simulations are expensive and they're slow, and so this works fine. But in this case, where the MD is super fast, yeah, of course it's the reading and writing files, it becomes a bottleneck, and so it slows down actually. So it's yeah, for this example, it's not a good way of communicating. Now, I must say we tried hard to do it with OpenMM, with MPI. Doing communication with MPI, which you can do, but it's a bit tricky, because then you need 2 layers of MPI, one for the normal, parallelization of your MD engine if you run with GROMACS or LAMPS or whatever, and then on top of that, the communication between the different replicas, the different walkers, right? Yeah, and that turned to be more tricky than we thought. So we can get it to work for one MD engine, for example, GROMACS. But then if you want to use another MD engine, like we also in the group use LAMPS and CP2K, then each has a different way of dealing with parallelization, and it became painful. And we wanted to have one version that works for all MD codes, so that we don't have to maintain, I don't know how many versions of PLUMED. And so this is what we ended up with. Okay, so that about the parallelization. We just, I go to directory number 1, change directory to run directory number 1. I start my plumed with an input file in the background. I go to directory number 2. I start the second one, and that one runs in that directory. Now let's have a look at what it looks like. The input file. Sorry, the plumed file. I mean. So both have now, both directives, the path CV and the method ID, have a couple of extra lines, and they all start with Walker, right? So there's a Walker ID 0 in both of them. There's two walkers, so both the path CV and the Metadynamics want to know about this information, so you have to put it both. You have to say where they will write their files. Well, I do one directory up, right? And how often do I write? Well, the Metadynamics potential is written from the other walkers every 500 steps, same as the pace, right? So every time it writes a Gaussian, it also wants to read the Gaussian that was done by the other walker. And the same for the path collector variables, right? It's updated every 1000 steps. Here I update the path, and then it wants to read also. Write it to a file and read it from the other walker. So that's how it works. Yeah, let's run it. See what happens. Now, one thing I noticed a few times is that it doesn't stop by itself, and it keeps waiting at the end for the other walker to finish. So let me quickly, you know what, I just kill it, I think, because it should have already stopped, right? Stop. Yeah, 1, 2, 1. Yeah, this is highly suspicious. Look at the size of my output file here. Pretty big, right? So this is, yeah, 0.3 gigabyte. And let's look in run 2 as well. Yeah, also quite big. So, and we can look in this output file. Yeah, so that's the problem with this this little example that is so fast that at the end, yeah, okay. So it ends with attempting to read the path from walker number 1. It's just waiting for the other walker, and so it's this disadvantage of doing communication through files if you're so fast and you're reading and writing so fast. Okay, so I throw out this.
Bernd, can I ask one thing?
Yes, go ahead.
So this was the exact same issue that I had. Can you check one of the hills files?
Yeah.
Because there was only Yeah.
Ah, okay. Yeah, that's a problem. Hey, that's weird because I think I had it working actually before.
Yeah. So this is the exact same issue that I had.
Hmm. Yeah. Ah. Oh, it's also only one path file. No, I wonder. Hmm. Can I fix this? Hmm. Okay, I'm not sure if I can fix this real time. I could put a sleep in it, I guess. If the first one wait for a moment for the second one to start. Yeah. Okay, so I don't know exactly what I did different this time. I've seen this before. Maybe I should write, just don't write so often. Okay, let me. Okay, I do one attempt to now fix this. If I don't manage, then I will put the solution online. Because I don't want to debug with it. Why can I not open this one? If it opening out of the. Is it open here? No. Okay, I don't know. Input. I will recover. Oh, okay, I think one flipped. Now let's try to write a little bit slower. Right, that must be it. But of course, this defeats the purpose. The idea is that we want to be faster using parallelization, not slower, right? So slow the update. But anyway, this is just an experiment. Let's say run 2. If then the problem still there. I must say it's not a problem if you run this with an MD engine where you just write every every second. But if you try to write a file 1,000 times per second, then yeah, get 20 conflicts. Okay, I'll slow this down by a factor of 2. Let's see if that's enough to fix it. I mean, I tested this last week, and then I was running like a charm, so I don't think I did anything different. Okay, here we go again. Yeah, now it's working, right? At least I have more stuff in my path files here. Sorry, path.0. You see, I have many paths now. Okay, so yeah, if you're writing too fast, then you get into trouble. But even now, it's not guaranteed that it's not going into trouble. Yeah, because I think at the end, it may still wait. But this file looks suspiciously big. This output file. Yeah, so this looks good, right? Okay, and then at step 2000, it's waiting for the other walker. And let's look at the other one as well. 1, 2. Yeah. Oh, this one. Oh, this is already okay. So they're out of phase. This one is at 4,000. And yeah. And so you can see here there are 2 copies of path out. So not only for each walker, which has a number, walker 0 and walker 1, but then there's one with an underscore. And that's already one trick to circumvent this problem. So it reads alternating to the one without an underscore and the one with an underscore, so to avoid, locked files. But yeah, so this is not the best example of the multiple worker things, because with such an analytic PES, with the PES MD, it's so fast that you get these conflicts. So it does work, but you have to slow down the reading and the writing. And then, of course, you undermine the whole idea of the parallelization, because you want it to be faster, not slower. So, anyways, yeah, so you can get it to work, but it's not going to be faster for this example. But yeah, we have some nice examples, and also you can find those examples in the plumed nest as plumed egg. If you search for the first author of the paper, which is Alberto, you will find them, and of course I also listed them in my slides from last week, which are online. And so there, and then you can see the examples, and they work like a charm. Okay, I think I stop here. I will put those. I will put the solutions online as well. I stopped sharing my slides, my screen, and I hope you could sort of follow this. I hope you got also pretty far, and I know Bas, at least you got all the way to the end, and then you're running these problems, which has nothing to do with anything you did. It's really this way of communicating so fast through files is not working, especially for this analytic example. Are there any questions left?
I have a question.
Yeah, please.
At the end, we have two files, right? At the end of the multiple worker, we have two files, but we must combine it.
No, they are in principle the same. There can be small deviations, because maybe the last one just read or still had to read the last update of the other worker or so. So there could be small difference because of the last step, but in principle, they are the same because they read each other's workers. And then, no, you don't need to update anything. You can read one or the other. It doesn't matter. They're the same.
Okay, thank you.
Yeah, it's just true for the FES and also for the path. They're both the same. Yeah. Are there more questions?
Yes. If you get a 1D free energy from the part CV, can you convert it back into like the 2D version? Like,
No.
there's no way to.
No, that's quite difficult. I mean, I think in theory you can do it. If you know exactly when you put the Gaussians, then you know at each time you know what bias you had, and then you can do like a umbrella sampling, right? So you build the histogram and you weight it for the bias that you already put, and you sample along, well, the correct variables that you haven't sampled, which in this case would be the Z direction. But no, I don't recommend doing that. It's really complicated, especially if the path is also moving. Then I think it's not possible anymore. Then it becomes too tricky. No, you cannot. Yeah, even if in theory it's possible, that's not the way to do it. Yeah. Okay, if there's no more questions, then
wait. Can I ask 2 questions?
Yeah, please.
So is this multiple Walker version also compatible with CP2K?
In principle, yes. Yeah, and I must say, we are using it at this moment in the group. We do have some problems that depend on the implementation on the version of CP2K. So with some versions of CP2K it works, and with some versions we cannot get it to work. Yeah, if you want, send me an email. I can tell you which version is it works. I must say I haven't used it yet on the Dutch national supercomputer, which we'll do probably in the next weeks, I think. We just got budget again to run on Snellius, but we are running it on Mare Nostrum in Barcelona, and there, yeah, it only worked for one version of CP2K. We needed the help from the local administrators to get it to work, because they also didn't understand why it wasn't working. And I think it's still a mystery why it only works with certain versions of CP2K, but yeah, it was problematic, and it's very strange because I mean it's communication through files. So how difficult can it be? But yeah. If you run into problems, then let me know, because then yeah, maybe I can direct you in the versions of CP2K that, for us at least, it was working. And
Okay,
in not too long, I should also be able to have to tell you how it works on Snellius.
yeah, sure. Yeah, that's because that's what I'm using as well.
Okay.
But then I have another question.
Yeah.
So most of the examples that I have seen have only, let's say, a starting state and a product state.
Yeah.
Would such a this path metadynamics also make sense if you have, for example, have two product states?
Yeah, absolutely, yes. So I didn't show you any examples today, but last week I talked about the multiple path version.
Yeah.
And so you can have several paths. And in the examples that I showed, and the ones that we tried out so far, they were just several paths that go from the same reactants to the same products. But that doesn't have to be the case, right? So they can also go. So if you have a landscape with A, B, C instead of just A, B, you can have a path from A to B, and a path from B to C, and a path from C to A, and you should be able to sample all the way around. It's yeah.
Okay. Yeah. Thank you.
Right. So if you think about the example that I showed last time with the polyproline, which is, so for example, the example with the tetramer, which had 3 torsions, omega-1, omega-2, omega-3, right? And you can say, I go from left-handed to right-handed, so either all the omega angles are 0, and in the other one they are all 180. So that's the reactant product, and they're the same. But of course, I can choose any intermediate and call that, C, let's say, right? And there's many intermediates. So it's all the corners of the cube, right? Except the reactant and product are all intermediates. So it's the same, right? It's just that, okay, I call them intermediates instead of other reactant and product states. But it's the same philosophy. So yes, no problem. That can be done.
Okay, well, that's all I want to know. Thank you.
Okay. Do you have more questions, Simona?
No, I'm quite.
Okay. Elena?
No, all good. Thank you.
Okay. Well, thank you guys. It was fun working with you, and I'm happy I could explain this stuff. It's always a pleasure. And yeah, if there's more questions, then the Slack channel will still be open, and we can discuss more. Have fun with this. I hope you do great science, and wish you a great day. See you around, guys.
Yeah, you too. Thanks.
Bye, everyone.
Bye, everyone.